Yeah, this chapter is about the search structures, which is about balancing trees. Okay. In this chapter, we're going to talk about binary search tree. Okay. And then when we talked about binary search tree, we didn't talk much about the balancing. So at the end of the chapter, I just mentioned about this balancing issue. So now we have to handle that issue. Okay. So in this chapter, we have three different kind of algorithms to balance the binary search trees. So first one is AVL tree. Okay, AVL tree is a binary tree structure that is balanced with respect to the height of subtrees. Okay, so we are going to focus on this tree, and then I'm going to mention what red-black trees and 2-3 trees. Okay, so binary search trees again. So now I think you are familiar with these trees. Okay, and it's basically from chapter 5. And binary search tree is a tree which may be empty or satisfy these items. First, every element has a unique key. And again, each element corresponds to one node, and one node has a key and data. And in this case, we need a left child pointer and right child pointer. But anyway, every element has a unique key. And keys in the left subtree must be smaller than that of root. And the keys in right subtree must be larger than that of root. And then recursively, left and right subtrees are also binary search trees. Okay, this is the definition of binary search tree. Okay, then what is the problem of binary search tree? This problem would be a motivation of AVL tree. Okay, so let's talk about the problem of binary search tree. And basically the performance of a BST depends on its shape. Okay, and the best case takes just log n, but worst case it takes n. So best case means if the binary search tree looks like this, is well shaped, is balanced, then the depth of this tree is log n, when n is the number of nodes. Okay, but worst case, if it is not balanced, if it is something like this, we have nodes here, and the depth of this BST is actually n. Okay, this is the worst case. So if it is worst case, we don't actually enjoy this BST. Okay, so to find one node, okay, if the target node is this one, then we have to go through all the nodes. It's exactly linear search. Okay, but if it is well balanced, then log n times comparison would be enough to find the worst cases here. I mean, in this BST, if these nodes are the target nodes, then it's the worst case. Okay, if the target node is around here, then maybe 2 comparison would be enough to find this node. But if this one is the target, that's the worst case for this case. Okay, and even with this case, if the target node is the first one, then just one comparison is enough. But when this one is the target node, then we need n comparisons. Okay, that is a motivation of balancing the BST. Okay, given a BST, then we want to balance this BST. Okay, let's talk about this best case for BST with some examples. Okay, so best case means the tree is well balanced. Okay, so let's try these keys. So we have 12 keys, and the keys are actually the strings. Okay, so we are not focusing on the numbers. Okay, so September is not 9 here. September is just September. This string is the key. So don't get confused. Okay, so September is larger than October. You know what I mean? So we are actually handling this one as a string. Okay, if the BST is well balanced, then the maximum number of comparison is 4. That's what I said in the previous slide, right? So if if our tree looks like this, then to find June or November or whatever, the worst case, 1, 2, 3, 4. 4 comparisons will be enough. And an average, if you calculate the average of comparisons to find out all the nodes, then it is 37 divided by 12, because we have 12 nodes here. And if we add up all the numbers here, 1, 2, 2, 3, 3, 3, 3, 4, 4, 4, 4, then it is 37. So 37 divided by 12 is 3.1. So on average, we need 3.1 comparisons to find our target node. Okay, so remember this 3.1. Okay, for the worst case, we have this linked list. This is a BST, but it's pretty much a linked list. Okay, so we don't use left child pointer at all in this tree. So it is a skewed tree, and we insert these nodes in sorted order. So this one was the first one, and we insert this one for the second time, and this one is third and fourth, etc. Okay, so this one is the first one, and this one is the smallest one, and the second element is second smallest element. So this one should be the right child, and when we insert this one is larger than the others, so it should be the right child of this one, and this one is larger than all the others, so this one should be the right child, etc. So we have a skewed tree. So with this tree, the maximum number of comparisons would be 12. Let's say our target node is September, SEPT. So we are searching for this string. Then how many comparisons do we need? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have to compare 12 times. Okay, then what is the average number? So we need 1 comparison for this one, 2 comparisons, 3 comparisons, etc. So we need 12 comparisons. So you know how to calculate this average, right? So 1 plus 12 divided by 2 is 6.5. So compared to this one, we have 6.5 times comparisons. It's kind of twice compared to the best case. Okay. But in this case, we have only 12 nodes. If we increase the number of nodes, then it will be way much more than the best case. Okay, not just 2 times. Okay, so we have a strong motivation of balancing BST. Okay, so now let's talk about the AVL tree. So AVL tree is balanced binary search tree developed by Edelson, Valsky, and Landis. So that's why we call it AVL tree. Okay, and AVL tree is a binary search tree satisfying this condition and this condition. So this condition is just recursive definition. So left subtree and the right subtree should be also AVL trees, like we did when we defined the BST, right? And look at this constraint. HL is the height of the left subtree and HR is the height of right subtree. And the difference between these two heights should be less than or equal to 1. Okay, so from this root node, this left subtree and the right subtree, they should have similar depth. Okay, they can be different, and we cannot force them to be the same all the time, because if we have 4 nodes, then there's no other way to have the difference of 1. Okay, so 1 is kind of the maximum here. So that's AVL tree. So it's kind of balanced. Okay. So to define this AVL tree, or to handle this AVL tree, then we want to define another kind of variable, a balance factor of a node T. Okay, balance factor is actually the difference between the two heights. That's a simple definition. Okay. And in AVL trees, BF of T should be -1 or 0 or 1. So look at these definitions. This part is actually BF, and the absolute of BF should be less than or equal to 1. It means BF could be -1 or 0 or 1. Okay. So, when we check all the BFs for all the nodes, if all the BFs are either -1 or 0 or 1, then it is AVL tree. So to make sure that this BST is AVL tree, then we want to check BF of all the nodes. Okay. So in this figure, BF is the difference between left subtree and right subtree when T is this node. And whenever we insert or delete a node to or from an AVL tree, the balance may be broken. Okay, so let's say we have this BST. Okay, so this is perfect. Then when we delete this node, what happens? To this node is okay, right? So left subtree has height 3 and this one has 2 and the BF is just 1. Okay, but to this node, the left subtree is 2, the right subtree is 0 because we just deleted this one, and BF is 2, and now this is not an AVL tree because we deleted this one. Or here, if we add one node here, then this is not a BST. Oh, sorry. This is BST, but this is not an AVL tree because this is longer than this. I mean, the difference between these two subtrees is 2. Okay, so anyway, when we delete or insert, it could break the balance, but sometimes it doesn't. Okay, so let's say with this BST or AVL tree, if we delete this node, then still this is AVL tree. Okay, and if we delete this one again, then still this one is AVL tree. Likewise, sometimes it may break the balance, but sometimes it doesn't. Okay, so if it breaks the balance, then we need rebalancing. Okay, to understand what AVL tree is, so let's check this example. So is it an AVL tree? Yes. How do we know? First, we have to check the BFs of all the nodes. So basically, the leaf nodes BF should be 0 because we don't have any child. Okay, and this one, BF of this node is 0 because the height of left subtree is the same as height of the right subtree. And this one is 0, but look at this one. The left subtree, the height of the left subtree and height of the right subtree, the difference between these two heights is 1. But still, 1 is okay. And this one 0, this one is -1. -1 is okay too. And 0, 1, -1, 0, 1, -1. Okay, so this one is an AVL tree, so there's no problem. But look at this one. This node and this node. The depth, the difference between the depths of this one and this one is actually 2, but to AVL tree is okay. So we don't care that because to this node, the height of this node compares the height of this subtree and height of this subtree. In this case, the BF is -1. Okay, so even though the difference between these two is 2, but we don't care. It is perfect AVL tree. So we focus on just the BF. Okay, so stick to the definition. Okay, now let's talk about rebalancing. So inserting a node into an AVL tree may break balance, then rebalancing is required. Again, we have strong motivation of this rebalancing, right? So if it is skewed, then we need more comparisons to find the target node in some cases. So we want to rebalance the tree. Okay, so let's say we have one node here, and obviously BF is 0, and we insert new node, which is May. And May is larger than Mar. So May is the right child. Then the BF of Mar is -1 and the BF of May is 0. Always, again, the BF of leaf node is 0. Okay. Again, we insert another node, Nov. So N is larger than M, so Nov is right child of May. Okay. Then it is a 0, and this one is -1 because 0 minus 1 is -1. And now Mar, the BF of Mar is -2 because 0 minus 2 is -2. Okay, so now we have a problem. So we have to rebalance the tree. How? So basically, look at this one. Mar is smaller than May, and May is smaller than Nov. Then if May is the root node, then Mar and the Nov are children. Then this is okay. So basically we rotate this to this. Okay. So to rebalance, we just rotated this tree. Okay. So this is basic idea of rebalancing. We actually rotate the whole tree, or sometimes some subtree. Okay, so let's try to insert all these nodes. Okay, so Mar, okay, May, okay, we have done this in the previous slide. Okay, so we have a couple of different cases. Okay, in this case we call it double R rotations. Double R means, we have a problem here, so we have a -2, which is a problem. Then to this node, right child is the problem. Okay, so we call it right rotation because we have right child problem. So double R rotation is about this case. So now we have perfect AVL tree. So now we insert the OG. OG is smaller than Mar. Okay, but still this is a balanced tree because when we check the BF of all the nodes, they are good. Okay. Now we insert another one, which is April. April is smaller than OG. Okay. Then there is a problem. So it's a 0, and this one is +1, but Mar has +2 as BF, and May has +2 as BF. Okay. Then we have 2 plus 2. Okay, then we focus on this one. Okay, the problem is coming from the left child. Okay, so we have a problem here, and from this node, left child is the problem. Okay, so we have left problem. So to rebalance this case, we have to rotate this subtree, and we call it double L rotations. Okay, double L means we have the problem in the left child. Okay, so the solution is quite simple. Just rotate as we did. So OG will be here, and April is left child and Mar is right child, and OG will be the left child of May. So we just rotate this subtree. And then what happened to this BF? By rotating this subtree, BF of this May becomes +1. So now everybody is happy. Okay, so BF is 0, 0, 0, 0, +1. That's double L rotation. So now let's try one more. So next one is Jan. So Jan is smaller than May and larger than OG and smaller than Mar. So Jan is here. So you know how to insert one node into BSD, right? So we have Jan here. But when we check the BF, this one is okay, this one is okay, okay. -1 is okay. But May has plus 2. So there is a problem. Where is the problem? So from this node, okay, so all the time, we focus on the node which has plus 2 or minus 2, okay. So from this node, left child, right child is the problem. So this one is plus 2. It means the left subtree is way much longer than the right subtree, okay. And then we have left child and right child. This one is too long, okay. And this one is LRB, left child, right child, case B. Okay, we have another case. Don't have it. Yes, we have left, right, C case here. And we're going to talk about left, right, B case, left, right, C case later in detail. Okay, so with some implementation. Okay, so for now, let's focus on that May has left, right problem. Okay. Then how can we rotate this broken tree? Okay, so this is a little complicated. Basically, mar is the largest element of this left subtree, and mar goes up to this node. Okay, and then this node is empty and gen goes up. Then may becomes the right child of this mar. So it looks a little complicated, but look at this rotation one more time. Let me explain one more time. Mar is the largest element of the left subtree, and it goes up, okay? And then gen should go up here. Okay, that's it. And then may is larger than mar, so may could be the right child of this mar. And we push this subtree as the right subtree of mar. Okay, so now we have well-balanced BST, AVL tree actually, and we insert the next node, which is DAC. DAC is smaller than mar and larger than OG and smaller than DAC and smaller than gen, so DAC is here. And when we check the BFs, and all the BFs are happy. Okay, so it's not broken. Now we insert July. Okay, July is smaller than mar and larger than OG and larger than gen. July is here. Okay, so there is no problem. All the BFs are happy. Next one. Excuse me. So next one is February, and when we insert February is here. Okay. Then when we check the BFs, 0, minus 1, 0, plus 1, minus 2 is here. And again, as I said, when we have a problem here from this node, we just inserted a new node here, and from this one, when we check, this one is the first problem, then we focus on this node, okay? And from this node, where is the problem? Right child, left child. Right child's left subtree is too long. So right left is too long, okay? So we have to rotate. Then how? Okay, so in the previous slide, actually we did pretty much a similar case. So in this case, the right subtree is too long. Then we have to pick the smallest one from this right subtree, which is DAC. Okay, then this one is the smallest one. Then it goes up. Okay, and then we push this subtree lower. Okay, so that goes up and we push down this subtree, and then fab will be attached to this. Okay, so just to focus on this part, okay, and that goes up here, and the OG and April, this subtree will be the left subtree of DAC, and then fab will be the left child of gen here. So since we actually moved this one to this place, then fab should replace this node. Okay, so basically we did pretty much the same thing in the previous slide, but actually it's kind of mirror case, right? So here we have left-right problem, and we have right-left problem. So it's exactly the same thing. So it's kind of mirror case. Okay, next we insert June. Then you know how to insert the node into a BSD. So we have June here. Then Mar has problem. Okay, all the other nodes are happy except Mar. Then where's the problem from this node? Left, right. Left, right has the problem. Okay, but this one is slightly different from the previous case. Let me explain the difference between the LRA and LRB and LRC rotations here. So LRA has something like this. So in this case, this one is the leaf node, or at least the BF of this node is a 0. Okay, and if the BF of this node is 1, it means we just added the new node here. Okay, that's why this one has +2. Then this is LRB case. And now we have LRC case. It means this one is -1. I mean the left right child has a problem. Okay, and I mean the problem is here. This guy has a +2 here, and if we check the subtrees, the problem is in the left subtrees, the right subtrees. Okay, and when we check this BF of this subtree, the subtree that has the problem. Okay, so when we check the subtree, if the BF is a 0, then is left right A case. If the BF is +1, then if it is left right B case. And now it is left right C case, which means the right subtree of this node is too long. Okay, so in this case, what should we do? First choice, how about the largest element of this left subtree of Mar? And the largest element is June. Okay, this one is the largest element. Then if we move this node, here, then what happens? Then Mar is larger than June, so Mar will be the right child of June. So think about this one. If June goes up, then June is here, then right child is Mar, and Mar's right child is May, and May's right child is Nov. So this one is not balanced. So June is not an option here. So instead, we actually choose this one. Okay, so Jan goes up, then what happens? If Jan goes up, then Mar should be on the right side, and at the same time July and June should be on the right side of Jan, and Feb should be on the left side. So Jan goes up, and Feb will replace this position. So now Feb is here, Jan is here. Then what happened to this subtree? These guys are smaller than Mar. Okay, so this one will be the left child of Mar. So we push this subtree down here, and at the same time these guys will be on the left side of Mar here. Okay, so let me repeat one more time. Okay, June is not a good choice. Instead, since Jan is the root node of this problem, so Jan goes up. Okay, and then Feb will replace this empty place. So now this left subtree is set. Okay, and Jan is here. And then what happened on the right side? Basically July and June, this subtree is on the right side of Jan, so it should be on the right side. It should be somewhere in this subtree. Okay, and then Mar should be on the right side of Jan. Okay, and we don't touch this part. And July was on the right side of this Jan, so now in this AVL tree, July is actually left child of Mar. So now when we look at these BFs, then all the nodes are happy. Good. So, and then now we insert another one, October. Okay, then do we have a problem here? And to May, right one is the problem. So we have double R rotations. So we just rotated this subtree. Okay, so the other part of the tree is the same. Only this part will be rotated. So now North will be the root node of this subtree, and then May should be the left child and October should be the right child. So now we have rotated subtree here. So now it's perfect. And if we insert September, then when we check all the BF numbers, it's perfect. It's an AVL tree. It's not breaking the constraint.